Good morning. It's nice to be here. So I'm going to talk about work that I did while I was at DARPA as a program manager and how it might be helping all of us be more safe and secure. So I'm sure you probably know that network computers are unacceptably insecure at this point. How many people have seen this picture of a Jeep in a ditch before? Raise your hands if you've seen this picture. Cool, so about a quarter of you. So I'll tell you a little bit about it. So this picture came about because two white hat hackers, Chris Falachek and Charlie Miller, convinced a Wired News magazine reporter, Andy Greenberg, to get in this Jeep Cherokee and drive it off near their hometown of St. Louis, Missouri. So I'd like to kind of picture that drive. So if you will, close your eyes and imagine you're driving in a car along a highway, and all of a sudden, your eyes are open while you're driving, just picturing it now. And all of a sudden, without you doing anything, the air conditioning comes on, full blast. And then the radio comes on, start playing a hip-hop station. And then the windshield wipers start going back and forth. And you're trying to turn off the air conditioner and turn off the radio, turn off the windshield wipers. And you're heading on this overpass, and all of a sudden your transmission cuts out. Your foot is on the gas, and the engine is revving, but the car is slowing down. You look in your rearview mirror, and there's a semi coming up behind you, a big, huge truck. That actually all happened to the reporter. Thankfully, he was able to get off the side of the road without causing any damage. The reason all those things happened was because Chris and Charlie were on their laptop at their house, and they were communicating over a cell phone connection to the car and telling the car to turn on the air conditioner, to turn on the music, to turn on the windshield wipers, to cut the transmission. All of that was possible because they had hacked into the car and rewritten some of the software so that it would respond to them and ignore the commands of the actual driver. So they did this on a Jeep Cherokee. They were reprising earlier work by Yoshi Kono from the University of Washington and Stefan Savage from the University of California at San Diego, where they showed essentially the same thing for a different car. They didn't publicize the make of the car because they felt like it wasn't really specific to that particular car, in the same way that these vulnerabilities were not particularly specific to the Jeep Cherokee here, but rather endemic to the whole car industry. So why is that kind of hacking possible? Well, it turns out a modern automobile is really a computer on wheels. A modern car has something between 30 and 100 what are called embedded control units, but an embedded control unit is really just a computer, and they're all connected to each other. And they control almost all of the functionality of the car, and really for good reason, right? The brakes are under software control because that allows them to implement anti-lock braking. The acceleration is under software control because of cruise control. And in those fancy cars that parallel park for you, the steering is under software control. The locks are under software control so that if you lock yourself out of the car, somebody else can open it for you and you can have the key fob open it up. For lots of good safety and security reasons, pretty much everything in the car is now under software control. And there are about 5 different ways that the network computer that is your car connects to computers that are outside your car. So for example, modern automobiles often come with a telematics unit. That's the thing that if you're in an accident, will arrange to call for an ambulance to come get you. It's the same service that if you get locked out and you call up the provider, they will unlock your car for you. That means your car actually has a cell phone number that attackers can call and get connected in to your car. There's the Bluetooth interface that allows you to connect your phone and your music system to your car. There's the entertainment system where you can plug in a USB drive. There's required by law, there's a ODB port underneath the steering wheel that allows a maintenance person to connect in and replace the software in the car. And then there's remote tire pressure gauges to communicate how much tire pressure you have that is another wireless network. So researchers showed that they could hack in through any of those interfaces and be able to take over and rewrite the code in the car so that somebody could call in through the cell phone and remotely take over control. And it's not just cars, of course, that have this property. Many, many systems have this property. Another wide area is another industry where this is common is medical devices, insulin pumps and pacemakers, for example. Daniel Lebert showed, for example, that he could wirelessly hack into his insulin pump and cause it to deliver incorrect dosages of medicine. And we've seen from sort of traditional network normal computers how easy it is to hack in and steal information. What's different with things like this car is now that the computer systems are actually controlling physical devices. And so in addition to stealing money and information, now they can cause physical damage in the real world. Okay, so why is it so easy to hack into these devices, right? Chrysler would really prefer nobody hack into their cars. Medical device makers would really prefer that people can't hack into insulin pumps. The reason why this is so hard is because the reason why there's so many systems that are so insecure is because it's actually really, really hard to build a system that is secure. You have to get absolutely everything right. If you screw something up, then there's a gate through which an attacker can break in. So like, there's so many things you have to get right. Even an octopus doesn't have enough arms to actually take care of everything at the same time. So that's why there's an octopus on the slide. So the first thing you have to get right is you have to get the overall design right. If you design the thing wrong in the first place, then you really have no chance of building a system that has good security. Then you have to document that design well. If you write down the specification, then people are going to build the wrong design, and again, it's very likely that there'll be security vulnerabilities. Then when you actually go to code it, you have to code it without introducing vulnerabilities. You get like no memory overflows, no underflows, no logic errors in the implementation. Also, you have to worry about side channels, or their ways of leaking information that are not through the normal computation, but through timing or power usage. Then you have to get the whole thing configured properly, right? You could have all of that done properly, and then you get it installed wrong. There's something wrong in a configuration file that leaves a security vulnerability. And then you have the problem that it's actually going to be used by human beings, and human beings are terrible security vectors, right? Like, people are really, really bad at doing good security. And one example of that is weak passwords. Right? People are terrible at coming up with strong passwords and changing them with the appropriate frequency and having them be sufficiently long. Also, people are gullible to phishing attacks, and phishing attacks are getting better and better as we have very clever adversaries who are able to mine our social networks to be able to craft messages that are very specific to us individually, that makes it very, very hard to not fall for a scam and click on a link that you shouldn't, that accidentally gives control of your system to somebody else. You have malicious insiders. You have to worry about the physical security of your devices. You have to worry about the hardware. Does it itself secure? And also, not only do you have to get everything right, but every third-party software system that you use, you have to make sure that they got everything right. And also, there's the challenge of misaligned incentives. So that goes back to the car company, or the computer industry in general, where the person who is paying for the security vulnerability, the person who pays for the fact that there was a breach, is not the person typically, or the company that wrote the software in the first place. So the company who's on the hook to write the software doesn't have very much incentive to put in the extra money to produce a system that is harder to break into, because they're not going to have to pay for the security vulnerability. The customer, the one who bought the software, who clicked on the license that said, this software is certified for absolutely no purpose, they're the ones who have to pay. So there's this misaligned incentive. If we could line up the person who pays the cost of the security vulnerability with the person who pays the cost of developing the software, then there would be more incentive to invest more in the security of the system. I think that this might come to a head in things like the medical industry or the automotive industry, right? Normally, car manufacturers are actually on the hook for the quality of their product. If they produce a car that has a systematic flaw, there are product liability laws that make it so that they have to pay the cost for that. In contrast, the software industry has gotten away for a really long time with saying, absolutely no warranty, this thing is good for absolutely nothing. So it'll be interesting to see going forward which industry's liability regime will be the one that holds sway. Will it be the computer industries, or will it be the car industries? If we get those incentives aligned, then maybe we'll, as developers, as system builders, we'll have more resources to address more of these things. So in this talk, I'm just going to talk about one of these security areas, just the implementation vulnerability issue. And I'm going to talk about some technique, or a technique, for improving our rate of writing software that has fewer errors. But it's only one part of the overall security picture. By no means is this a silver bullet, even just for the implementation errors, but definitely not for the whole security picture. Okay, so why is focusing on implementation errors a worthwhile thing to do? So it turns out there are many exploitable vulnerabilities. So VulnDB is a database of vulnerabilities. They keep track of how many vulnerabilities are reported each year. And for all those vulnerabilities, how many of them have public exploits available. So this is a report that they published in mid-2018, so the middle of this year. They had kept track of 10,599 vulnerabilities. And of those, 41% had public exploits available, or very close to a public exploit. So some vocabulary. A vulnerability is a bug in the code. An exploit is code that leverages or takes advantage of that vulnerability in order to make the system do something nefarious. So vulnerabilities are annoying. Exploits are something you have to worry about. And what this is showing is that many vulnerabilities are actually exploitable in a way that is publicly known. So, and then those exploits can do things that we care about. So for example, the Microsoft Security Bulletin MS-1578 Critical talks about a remote code execution flaw that was published in July 2015. It came about because there was a buffer underflow error, so a coding error in the Adobe Type Manager library. And this vulnerability allowed an outside hacker to get remote code execution on every single platform that Microsoft supported in 2015. So if you were running any Microsoft system, an attacker could use that vulnerability to take over remote control of your system. Similarly, in addition to taking over control, there's also the ability to exfiltrate information. So the Heartbleed bug was a missing bounds check, so again, a coding error in an implementation of OpenSSL that allowed the theft of sensitive information. So your password and other kinds of information, bank account information on your computer, in a way that left no log information. So there's no record after the fact that any information had been stolen. So this slide makes the case that vulnerabilities that are converted into exploits can do things that you don't want them to do on your system. So they're things we need to worry about. Now, converting a vulnerability into an exploit is not easy. In fact, it's incredibly hard. Just the sheer malicious cleverness of hackers who are able to convert vulnerabilities into exploits is off the charts unbelievable. Like, I really wish that all that energy was going into productive things instead of finding vulnerabilities. So you could say, well, there aren't that many people on the planet who have the skills to be able to convert vulnerabilities to exploits reliably, which is true. But some of them, in addition to their hacking skills, are also entrepreneurs, and they can package up exploit kits and make them available on the web. So for example, the Phoenix exploit kit from 2010 packaged together 10, 12 different vulnerabilities to be able to make a software package that you, if you didn't have these hacking skills, you could just go buy it and then use it to steal information and take over control of systems. So this enables large numbers of people. Now all you need to do is have money and have the ability to go find a website and pay the money to get the tool, and then it has a nice dashboard and user interface to have you do this. Right. So we have a pretty big problem. We have more and more systems that are network computers that connect with the physical world that we would like to be secure. And there's an ecosystem out there that makes it relatively easy for hackers to break in and steal information or cause damage. So let's do something about it. So the hypothesis of the work that I'm going to talk about today is that formal methods can eliminate many of these exploitable vulnerabilities. They will allow us to build software that doesn't have so much low-hanging fruit that hackers can exploit. So if you've been around for a while, your reaction to that is probably like, oh my God, please give me a break. I've heard that story forever. Right? The formal methods community, in fact, has been in existence since basically the beginning of computer science, and has indeed been promising that formal methods would be able to produce software that doesn't have vulnerabilities for more than 50 years. And for almost the totality of that 50-year period, their promises have not lived up to the hype. They haven't been able to do anything on systems of sufficient size or complexity to be interesting beyond the pure academic interest of could you do this or could you not. But I would say that now, in fact, is a really good time to revisit that hypothesis, to see, in fact, if now is a time when formal methods really can start to deliver on their promise. So there are 4 reasons at least why I think now is a good time. The first is just Moore's law. This slide is basically showing the improvements in transistors and clock speed and power from 1970 to 2010. Of course, it's showing that this is trailing off, but decades of exponential growth have produced computers that are way, way, way more powerful than the computers were when people started doing formal methods research. And it turns out a lot of formal methods research is just fancy search. And the bigger the computers, the more memory you have, the more cycles you have, the more efficiently you can search space. So just being able to search more effectively, just having more powerful computers is one of the significant factors that makes formal methods much more impactful today. A second thing is that formal methods researchers have actually been making really fundamental improvements in their tools. So how many of you know what a SAT solver is? If you know what a SAT solver is, please raise your hand. Cool. So most of you do. So a satisfiability is the problem of you're given a Boolean formula. So a Boolean formula is a formula where the variables stand for true and false, and they're connected via and, or, and not. And the satisfiability problem is coming up with a truth assignment to those variables that makes the overall formula true. That sounds like it's an NP-complete problem, so there's no known good solution. So for a long time, the problem was not that interesting because it was like, okay, yeah, we can't solve it except with an exponential algorithm. We don't care. But it turns out that there are many heuristics that allow you to solve satisfiability problems in many, many cases very, very quickly. And that's useful because many questions that you want to ask about software can be converted into Boolean formula. And then the satisfiability of the Boolean formula tells you something about the code. Now that encoding is extremely verbose. Every bit in the Boolean formula every variable in the Boolean formula corresponds to one bit in your computer. So you can imagine how big these formulas are. But nevertheless, because computers are so good at solving these kinds of formulas now, it can automatically prove interesting properties about programs. So what this slide is doing is showing how much SAT solvers have improved over a period of about 15 years. So here the horizontal axis, so there's a competition every year where everybody in the world who is working on SAT solvers submits their solver, or at least the ones who want to participate in the competition, submit their solver. The people running the competition come up with a whole bunch of problems, and each solver gets run on all those problems, and you get points for every problem you solve, and the team that wins the competition is the one that solves the most problems during the 20 minutes of the period of the competition. So what this graph is showing, the horizontal axis is the number of problems solved, from 0 to 180. And the vertical axis is how much time it took to solve that particular problem. And each line corresponds to one solver. So as soon as this particular solver solves a particular problem, it gets a little tick mark. And so the ones that go up really fast are the older ones, that it took them maybe 1,200 seconds to solve 40 problems, say. So if we just look at the point here of how long did it take to solve 80 problems, and look at the solver from 2002, it took 1,000 seconds to solve 80 problems in 2002. Whereas in 2010, the best solver, it only took 40 seconds. So that's an improvement of almost 2 orders of magnitude in how fast you could solve these the SAT problems. And that's on top of the hardware improvements that already happened, because all of these solvers were run on the 2009 problem instance on a computer that was current as of 2010. So they were all running on exactly the same hardware, modern hardware at the time of 2010, all running on the 2009 problems. So the automation has improved dramatically on top of the hardware improvements. And this was all done to work that Daniel Lebert did. Compiling this graph was enormously valuable, because this graph was one of the things that allowed me to convince DARPA that it should invest in this area. So thanks to Daniel. A third reason why formal methods are much more able to be effective now is that the ecosystem of formal methods tools has advanced significantly in the last 50 years. So at the beginning, when those formal methods researchers were talking about how they could use formal methods to prove interesting properties, the same researchers who were working on advancing the formal methods were also then working on trying to apply those formal methods to real-world problems. And it turns out both of those were full-time jobs. They didn't have enough cycles to be able to simultaneously improve the formal methods tools and apply them to real-world problems. But that's very, very different now. Now there are many, many tools that are open source, that are available online, that have documentation, that have tutorials, that have courses you can take, that have textbooks, so that people who are not the formal methods, the people who are doing the research in the basic methods and formal methods can use these tools and techniques for their own purposes to work on software. So this is just showing a smattering of some of these formal methods tools that are now available for widespread use. And then I would argue that there's one more factor that is contributing, and that is that the scale of the problems are getting to be so high that people know that they need help in order to solve these problems to acceptable standards. For example, at Amazon Web Services, they are worried about their distributed systems, right? They provide an infrastructure that people all over the world use, and a 1 in a million event for them is something that happens like more than once a second. So humans are really good with our intuitions of things that happen all the time, but something that happens 1 in a million, that's like never as far as we're concerned. But in Amazon Web Services time, that's all the time. Their systems have to work to way, way, way more than 1 in a million level of confidence. And what formal methods tools allow them to do is drive the system into all the weird corner cases and make sure they've thought through what's happening in those weird corner cases. So there's a growing acceptance that we need to have better and more powerful tools in order to help us make systems that are more robust and have higher levels of correctness. Okay, so some evidence, the DARPA HACMS program. So the idea here was to test this hypothesis, that formal methods could be applied to produce software for vehicles that were much harder to hack into. So here the threat model that we were interested in was the attacker knew everything about the system, had full access, like knew all about the code, knew all about the design, but did not have physical access, had only remote access. And the reason that was the threat model was because if you have to physically touch the device, then there's only so many systems you can compromise. Whereas if you can be remote, then you can touch anything that you connect to. So the scale of the threat is much bigger from remote access than with physical access. We assumed that the hardware was correct. We know that's not a good assumption, but you can only solve so many problems at once. So for the purposes of HACMS, we assumed that the underlying hardware was correct. And then we worked on a couple of different platforms. So we took a quadcopter, an RGCopter, something that you could buy from Amazon. All of the source code is open source. It was about 100,000 lines of code. All of the researchers working on the program were able to have full access and could see all of the code with no restrictions. And then we had a partner vehicle, which is this Boeing unmanned little bird, the ULB, which is a full-sized helicopter. It's big enough to have up to 2 pilots. It also can be fully autonomous, so it can fly without any passengers, any pilots at all. And the goal was to explore the security of these 2 platforms. So I'm not going to show the video, but what this video is showing that the researchers were able to hack into and take control of the quadcopter with absolutely no difficulty. There was an off-the-shelf cracking tool called air cracking that would allow them to scan the network, figure out how to connect to the quadcopter, disconnect the legitimate owner, and then have the quadcopter fly off into the sunset, as it were. And this was done by the blue team, the formal methods researchers, not the red team, the people who were experts in penetration testing. To assess the effectiveness of the formal methods tools, we also paid a red team, a world-class red team, whose job it is to break into systems. So at the beginning of the program, for a baseline assessment, the red team attacked or broke into or tried to break into the quadcopter and Boeing's unmanned little bird. And they were given full access to all the documentation. And perhaps not surprisingly, they had no trouble doing this, particularly for the quadcopter, which I think the main concern of the manufacturer for the quadcopter is that it was flying in the park and there was no one connected to it, as opposed to worrying that your neighbor might be able to hack in and take over control of your quadcopter and steal it from you. So the red team was able to take over control of the quadcopter. A little bit more surprisingly, they were also able to hack in and take over control of the unmanned little bird. The Boeing engineers were extremely surprised that that was the case. So the baseline is at the beginning of the program, red team was able to break in, take over full operations of both the helicopter and the quadcopter. So then, during the first 16 months of the HACMS program, the blue team, the formal methods researchers, went to work re-engineering, re-implementing the software for the quadcopter. So this chart kind of shows a notional chart of how they developed it, with time going this way. And at the bottom, here's an architectural sketch of what's going on. So they start out with the monolithic software. There's no real-time operating system, and there's no security in the original platform, which is why the red team had such an easy time breaking in. They refactored the architecture. They changed the underlying processor so it was a little bit more powerful. They then put in a free RTOS layer, and on top of that, a hardware abstraction layer, so that this software didn't need to know if it was running on this chip or the original chip. And then they got to work replacing these pieces with high assurance versions. So they worked on replacing the free RTOS with a verified real-time operating system out of Data 61 in Australia. they started rewriting the flight control software, the things about the stability control and the altitude hold, the thing that makes the quadcopter actually be able to fly. They wrote it in a domain-specific language in Haskell that would then generate the low-level C code along with proofs about that code to verify that there was no overflows or underflows, things like that. And they kept working on that. They also started generating the glue code that would connect all these pieces together from high-level system architecture diagrams that were connected into a proof system where they could prove properties about the underlying system. So at the end of 16 months, they were responsible for handing over the new design to the red team for assessment. They were able to implement stability control, altitude hold, directional hold, and a new denial of service detection module. They were only able to get about 80% of the GPS waypoint navigation implemented. So they got about 80% of the functionality of the original quadcopter done in that first 16 months. Overall, they wrote about 80,000 lines of high assurance software in phase 1. Then they proved system-wide security properties in a machine-checked kind of a way. They proved that the system was memory safe. They proved that any messages that had arrived from the ground control station, if it was not well-formed, were just dropped and ignored. They proved also that messages that weren't authenticated properly were going to be dropped and ignored. And they proved that any message that was received by the quadcopter, that was well-formed, and that was properly authenticated would be appropriately acted upon. They couldn't prove that every message that was sent was acted upon because there's a possibility of jamming where an adversary would stop the message from being able to get through, but they proved that if it got through, it would do the right thing. The red team then they were able to be full partners in this whole design process, so they knew as much about the system as was possible to know about the system. They knew all about the architecture, they knew about all the software, they had access to all the software, and they had 6 full weeks to break in again, to repeat what they had done at the very beginning of the program. And at the end of that 6 weeks, they were not, in fact, able to break into the system or disrupt its operation in any way. My colleague at DARPA at the time, who was a penetration testing expert, that's what he did before he came to DARPA, his assessment was that that UAV at the end of 16 months was the most secure UAV on the entire planet, which is a little bit scary if you think about what UAVs are doing on the planet. And all the code is available open source. Okay, so that was after the first 16 months. At that point, my boss at DARPA basically told me that DARPA thought that result by itself fully justified the entire program. That was a success that was worth the $70 million investment that DARPA made in HACMs. And he also told me that, by the way, they had thought the program was going to be a total failure, right? They didn't think it was possible. So we succeeded, the researchers succeeded in 16 months doing something that DARPA thought was impossible. So that gave them 2 more phases, so another 3 years to do more good stuff. So they continued to work on taking the tools and techniques from the quadcopter and applying it to Boeing's unmanned Little Bird, among other things. They also started working on a whole bunch of other platforms with the goal of getting as many exemplars as possible. So the quadcopter, open source, everybody has access to it. The unmanned Little Bird is IBM technology. It's proprietary, it's ITAR restricted, which means that really only the Boeing engineers were able to see the software or operate on that software. So they had to learn the tools and techniques that the formal methods researchers had developed in order to apply it themselves. So there's kind of a built-in tech transfer here. So the architecture of the unmanned Little Bird is a little bit more complicated than the architecture of the quadcopter. Instead of one processor, there are 2 processors. One of those processors is the flight control computer. That's the thing that worries about altitude hold and stability, keeping the helicopter flying as a helicopter. And then the other one is the mission control computer. The mission control computer is responsible for talking to the ground station, for talking to the flight control computer, and for deciding, telling it we should fly over there, we should take this picture, things like that. So the flight control computer ended up having a software stack that was very much like the software stack that we saw on the quadcopter in phase 1. The mission control computer at the bottom layer, they ran SEO4 microkernel, which is a fully verified microkernel that was produced by Data61. It allows you to partition the software so that you could have different partitions, and provably those partitions cannot interfere with each other. There's no information exchange between them, including they've analyzed at the level of timing to make sure there's no timing information that's flowing between them either. So they configured it so one of those configurations was responsible for talking to the ground station and for talking to the flight control computer. And they verified all of the software that was in that partition. So that's the authentication code, the crypto code, things like that. They proved to be functionally correct. they set up another partition where they put the camera software and all the kind of other legacy software that they didn't have time or didn't want to verify. Then, to do the red team assessments, they allowed the red team, they gave the red team a head start. They let the red team put whatever code they wanted in the camera partition, the legacy partition. And they let the red team run in that partition with root access. So basically, red team's already there, whatever code they want to run at root access. And they challenged the red team to break out of the sandbox or to disrupt the operation of the helicopter in any way. At the end of phase 2, they did this test while the copter was on the ground. At the end of phase 3, they did this test while the helicopter was flying. They were so sure that the proofs were going to hold that they allowed the red team to attack the helicopter while the helicopter was in flight. And the red team was not able to disrupt the operation of the helicopter or cause any disturbance whatsoever. And the safety pilots who were in the helicopter while this happened reported that the helicopter flew exactly as if it had been not running high assurance software. So there was no degradation in the quality of the flight, but the red team was not able to break out. All the red team could actually do was crash their own partition by fork bombing themselves. So every once in a while, when the red team decided to fork bomb themselves, the camera partition would go down. There was monitoring software in one of the other partitions that would say, hey, the camera just went down again, let's restart it, and it would come back up again. So there was no degradation to the flight of the helicopter. So this was fantastic, like super surprising, super fantastic result. Which the hope here is that we create a virtuous spiral where there are procurement officers in the Pentagon who write requests for proposals. They want to go buy some kind of new device. They write a description of what it is, and then they publish it for companies to bid on the right to make that new device. So the hope is that those procurement officers will write into the requirements that you must prove that certain parts of your system are functionally correct. You must prove that there are no memory safety violations. You must prove that the communications is secure. All the same kinds of things that the blue team proved about the helicopter. Now, before HACMs, the fear would be that the companies would come to those procurement officers and say, oh, come on, that's ridiculous. Nobody knows how to do that. If you put that in there, nobody's going to be able to bid on this. You're not going to be able to get any responses. If you want this widget thing, you got to take that part out. But now, after HACMs, the procurement officer can say, like, what are you talking about? These grad students did it. If these grad students can do it, why can't you do it? And so the hope is that those requirements will be left in the procurement documents, and then the defense contractors will be like, okay, we have to do this, so let's go hire some of those grad students and develop the expertise in-house to be able to do these kinds of techniques so that we can successfully win these bids. And then they will have in-house the expertise. We'll have enlarged the ecosystem. There will be more people who know how to do this. The tools will have better support so that they can apply them to other kinds of things like insulin pumps and pacemakers and the doors on prison cells, for example, all of which are known to be vulnerable. So just this past year, there was a law passed in Congress in the US and signed into law, the John McCain National Defense Authorization Act, which directs the Pentagon to explore using HACMs-like technology to produce systems that are much harder to hack into. So the hope is to get that virtuous spiral going. Okay, so that was the HACM story. So I've been mentioning formal methods over and over and over again, but what do I actually mean by formal methods? So I looked around for a definition of formal methods, and the best one I could come up with was this one, which is on the web from Jean-François Monin in 2003. He says, formal methods are best described as the application of a fairly broad variety of theoretical computer science fundamentals to problems with software and hardware specification and verification. So basically, tools to do stuff about software, not particularly useful. It's one of these things I think is like you know it when you see it. But the characteristics are it's based on math, it's machine checkable, and it's capable of proving properties about both code and models of software and hardware. But it's really important to read the fine print. All of these proofs come with assumptions. If you don't satisfy the assumptions, then the theorem doesn't say anything. And the guarantees, what it tells you about the system can be too weak, right? Just proving that something is memory safe doesn't mean that the system does what you want it to do. So there's actually a whole range of formal methods techniques that are consistent with that definition. So this chart gives a notional definition. The horizontal axis is how hard is it to use or how much effort is required. From the left-hand side, it's fully automatic. To the right-hand side, it takes PhD years per 1,000 lines of code to accomplish anything. The vertical axis is how strong are the guarantees. The bottom, you have pretty weak guarantees, like type safety. And at the top, you have full functional correctness, and potentially correctness with respect to side channels as well. So here, down at the bottom, we have type systems, right? Any type system is, in fact, a formal method. It's a way of proving properties about the code. You prove that this code is going to return an integer, for example. So there's type systems, and then you have things like symbolic execution, model checkers, static analyzers, runtime monitoring that's verified, automatic theorem provers, and then at the very top, interactive theorem provers. And all of these different kinds of formal methods have been used to prove properties about interesting real-world systems. Things from down here, like the simple end of bind, which is part of the domain name server that keeps the internet running, all the way up to the top where you're proving things about the SCL4 microkernel, CompCert Verifying C Compiler, and so on. Okay, so one of the lessons of the HACM's helicopter experience is that you don't actually have to verify all the software in the system. There are certain exquisite artifacts that if you verify those particular exquisite artifacts, you can put them together and architect much larger and more complex systems that have much higher security guarantees than the software that we typically deal with today. And if you think about, like, what kind of software would be worth verifying, things come to mind like separation kernels, hypervisors, real-time operating systems, C compilers, garbage collectors, file systems, web browser soundboxes, and various kinds of cryptographic primitives. And the really good news is that in every single one of these categories, there are already systems out there that have been published in the literature that do full functional correctness proofs about those particular artifacts. So I just want to drill down into two of them. The first is the SCL4 microkernel that I've been mentioning. So what is a microkernel? It's an operating system, but it's a super squished down, pared down operating system. It's the core most part of an operating system that absolutely positively has to run in privileged mode. It's about 10,000 lines of C code, and it's been implemented and fully proven correct in Isabel Hall by Data61 team in Australia. As I said, it's about 10,000 lines of code, and it's about 480,000 lines of proof. So that's a huge imbalance, right? It turns out that piece is an outlier of all the formal method systems all the systems that I've been showing you that have been proven functionally correct. This is way, way, way more higher level of effort. I think part of that is because of the nature of a microkernel. It's a rat's nest of stuff that's connected to each other. So this is the control flow graph of SCL4, so 10,000 lines of code, and like basically everything is connected to everything else. You can't really nicely separate out the pieces. So that's, I think, one of the reasons why the level of proof is so high. Another is, if you think about it, how do you specify correctness for a microkernel? It's actually pretty tricky to write down what it has to do to be correct. So even the specification is reasonably complicated. It took them a little bit over 20 person years to write the code. 13 of that was dedicated to the specific proof for the SCL4, and about 8 was infrastructure, libraries, and tools that would be more generally useful. So they estimate if they had to do it again, it would be more on the order of 13 person years rather than 8 person years, or 21 person years. And that person year total is also a kind of an outlier and is related to that 480,000 lines of code. It turns out, just the same way that software engineering lines of code is a good predictor of how much time it takes, same thing with proofs. The amount of lines of code in the proof is a reasonably good predictor of how long it will take to prove it. In terms of the speed, it's the fastest known one-directional IPC fast path in its class. So it's no slower than the competition. In fact, it's faster than the competition. And what they proved is they proved that the SCL4 provides the access control enforcement. That's the thing that allows us to separate out the partitions and have the camera software and the high assurance software be completely separated from each other so that the camera can't infect the high assurance software. They also proved so they proved everything at the level of the C code first, and then they separately proved that the generated assembly code that corresponded to the C code had the same semantics. So all of the properties that held to the C code actually hold to the assembly code as well. And then they proved the correctness of the fast path, which was a special path through the code. And it's all available open source, so anybody can take it and use it and extend the proof. The other artifact that I wanted to drill into a little bit is the CompCert Verifying C Compiler that was written by Xavier Leroy at INRIA. It's not all of C. It doesn't have the concurrency pieces, for example, but it has all of the C that's necessary or that is used by the aviation industry. Xavier implemented and proved CompCert functionally correct inside COC. Here, the proof and the code together was 42,000 lines of code. So you can see that's much, much smaller than the effort for the SEL4 proof. And it only took 3 person years. Of course, that is Xavier Leroy person years, and he's not a mere mortal when it comes to writing code, so you probably have to inflate that a little bit. But still, a much more reasonable level of effort. And I think part of the reason why the effort was lower is if you look at the architectural diagram of the CompCert Verifying C Compiler, you can see it's basically a nice pipeline. Every red box there is one square in the pipeline of the compiler, and you could prove each one correct in turn. So you have a nicely partitioned proof, so you get much better separation. Also, the specification of what it means for a compiler to be correct is very simple to write down, as opposed to the specification of a microkernel. The speed is a little bit slower. It's 2 times as fast as GCC with no optimization, but it's 7% slower than GCC with level 1 and 12% lower than GCC with level 2 optimization. Okay, so why isn't everybody already using formal methods? I'm sure you know the answers to these questions, but drive in a little bit here. So one is the problem of expertise. So this reports on a survey of formal methods researchers in 2006 that was actually reported in 2009, counting how many people were there in the entire planet who knew something about formal methods. And in 2006, the answer was less than 5,000 people in the whole world, right? Compare that to the number of Java developers, right? However, I think this is moving in a positive direction. There are many more courses now. There are many more universities that teach courses in formal methods. We might be even up to like 15,000. So we're going fast. We're increasing at a fast rate, but we're starting from a very low point. So then there's the issue of the required level of effort, right? If you have to, writing the code is one thing, but if you have to write the code and you have to write a proof, it's like doubling your effort, it seems like. And it is true that the amount of time to develop a formal methods-based system along with a proof takes more time. So this slide shows a bunch of different systems that have been verified to be fully functionally correct in the past 10 years, how big they were and how long it took. So we can see here that CompCert is indeed an outlier with 480,000 lines in 21 years. Like the CompCert is the next most complex at 42,000 in 3 person years. And some of them down here are much, much lower, like less than 25,000 lines of code and less than a person year. So depending on what the artifact is, we're at a place where the level of investment required to produce high assurance software is really worth the investment, particularly for things like crypto. Like if we go back here, I don't think it's an accident that there are so many things under the crypto side here, because crypto is all about having high assurance in your software, knowing that what the message was is knowing what the message was intended to be is what the message was is really important. And so the effort required to do the verification is worth it. Okay, so overhead. Then a second issue is performance consequences. It's often the case that the formally verified system is slower than the non-verified system. Now, part of the reason for that is when you have a system with super high performance, a lot of the reason why there's super high performance is because somebody went in and measured why was there bad performance and put in special cases, put in fast paths. So every time there's a fast path, that's another path through the code that has to be verified separately. And the teams that are coming in and doing the verification, basically they stop as soon as they get a system that's fast enough for their purposes, and then they don't actually go through and do the rest of the verification. So for example, with the SEL4, originally it was a little bit slower than the competition, but they just kept going back and working more until now they have a fast path that's faster than the competition. So the SEL4 is now the fastest known. CompCert is still slower. So then Amazon Web Services is now running a verified version of parts of the TLS protocol. The HMAC, the DRGB, and the TLS handshake are all formally verified. So in Amazon's estimation, the performance is good enough that it's better to run the verified version than the non-verified version. Similarly, the P256 elliptic curve crypto algorithm that is used in Chrome, Android, and Cloudflare is now the one that is formally verified. And the Hackle crypto that is used in Firefox is formally verified. So we're getting to the point where the formally verified versions, even if they're not faster than the non-verified version, they are fast enough to be used, and with the verification guarantees are worth any performance degradation that remains. Okay, so then not only is the performance of the final product important, but the product lifecycle is really important too. How long does it take to get to the market, to get the code out there? So in certain, particular industries, you have to get the code out really, really fast, and if you have to do a proof that slows down the development, that can be a big impediment. So we're also seeing advances in formal methods being able to be incorporated into the normal development tool chain. So for example, Facebook bought a company that does static analysis, and they're now able to analyze all of the code in the Android and iOS code base for Facebook in less than 4 hours. So the 4-hour number isn't that important. That's longer than the normal development cycle, but it can take place overnight. The part that's really important is the 10-minute number, which means you're a developer, you want to check, you go to check in a change, you check it in, and it gets this analysis, runs over it automatically, and it comes back and tells you, yes, this is okay, you can go ahead and finish the process, or no, this failed our check, you have to go back and fix whatever the issue is. So the trade-off here is that, okay, they're going to tell it to you really quickly, but what they're going to tell you is just the absence of null pointer errors and resource leaks. So on that graph of level of effort and versus how much you get to know, what they're telling you is relatively weak property, but they're telling it to you automatically and really quickly. Also, the effort at Amazon Web Services. So they wanted to prove functionally correct the HMAC digital random bit generation and TLS handshake part of the TLS protocol that is being used by all of their Amazon Web Services clients. So the top part, they have a proof of functional correctness for those pieces of the protocol. At the highest level, there are statements about math and crypto that haven't changed in, this changed once in 20 years. But then you take that high-level statement of math, and then you map it down into code, and then you map it into high-level code, and then you map it down into the low-level implementation. The low-level implementation actually changes fairly frequently. And what they did was they set up a proof system so that if a developer makes a change in the low-level implementation of any of those protocols, it reruns the proof. And only if it can't automatically reestablish the correctness of the proof does it go back to ask the proof engineer to fix it. So this re-verification typically takes less than 10 minutes. So again, the developer gets feedback about whether their change was accepted or not in a time frame that's consistent with a normal development process. In the last 12 months, they replayed the correctness proof 956 times. That means 956 times somebody checked in a change that actually potentially impacted the correctness of these protocol implementations. And in those 956 times, only 3 times was the system not able to automatically update the proof. Only 3 times did a person have to go and fix the proof. Okay, so then we get to the fine print. So as I said at the very beginning, all of these proofs come with assumptions. And if you don't satisfy the assumptions, then the proof doesn't actually say anything. So we talked about CompCert and how it was verified to be fully functionally correct. But John Rager, who's a researcher at the University of Utah, works on compiler correctness. He built a tool called CSmith that basically does testing of compilers. And he reported in PLDI 2011 that he found 325 bugs in a variety of C compilers, including CompCert. Which, wait, CompCert's formally verified. How is that possible? Well, the bugs that he found in CompCert, one was in the parser that hadn't been verified, and the other was that the model of the hardware didn't exactly match the real hardware, and there was a vulnerability there. The unverified front end has subsequently been fixed, so that bug is no longer there. Of course, the issue with the hardware mismatch is continuing. Things like Spectre and Meltdown are examples of where the hardware and the models of the hardware don't match in a way that can be exploited by an attacker. John Rager's comment in the paper is the striking thing about the CompCert results is the middle-end bugs we found in all of their compilers are absent. CompCert is the only compiler we have tested for which CSmith cannot find wrong code errors. Basically, there were no mistakes in the middle of the compiler. And that was not for lack of trying. They devoted more than 6 CPU years to trying to find a bug in the compiler without success. Okay, so where do we stand? So there's some lessons to be learned here. Right? One of them is the lesson from Hackams, among other places, is don't verify all the code. Just focus on the code that you need in order to establish the end-to-end security vulnerabilities that you care about. Right? You don't have to verify the camera software. You just have to verify the communication software and the architecture communications to make a system that is separable and that the red team can't attack successfully. Another lesson is to leverage automation, like the AWS system that can automatically read you that proof And so the engineers don't have to worry about it, but the system can fix it for them. There are obviously many ongoing challenges, though. So, for example, one of the challenges is the getting buy-in and adoption. There was the researcher at Amazon Web Services who really wanted to use formal methods-based techniques, specifically model checking of the architecture of a distributed system to figure out if there were vulnerabilities in the Amazon Web Services system. He got really excited, and he talked to another one of his engineers and got that person really excited. And they were like, absolutely, we have to get the rest of the team using this. How are we going to do this? They decided to have a seminar, a training tutorial for a day about using model checking to find these kinds of problems. But they were really worried about the term formal methods. They thought that just saying the word formal methods would turn their colleagues off. And so they didn't, in fact, say the word formal methods at all. Instead, they talked about it as exhaustively testable pseudocode. And indeed, at the end, there were lots of people who were like, wait, I need to use that. Tell me how to use the exhaustively testable pseudocode. So they got buy-in, and now they've been using it since that work. There's a really nice white paper that the team wrote about the decision to adopt this tool at Amazon Web Services. Another really important challenge is incorporating hardware issues. Right? So all the recent press about Spectre and Meltdown and Rowhammer, those are all places where you can trick the hardware into like the interface that the hardware promises it's providing and the actual information contents that's leaking through are not the same. And so the hardware can be exploited to exfiltrate information, for example. And so there's a lot of work that needs to happen at the hardware-software boundary. Part of the good news there is that the hardware also has formal descriptions that are suitable for analysis by formal tools. And then the two elephants in the room are handling concurrency. Right? All of the systems that I've talked about so far do not have concurrency. They're just single-threaded. And concurrency makes the things much, much, much harder because it produces a combinatorial explosion of possible states. And so this is an active area of research where there's still lots of work to be done. Okay, so is this goal within reach? Is it possible that we can have now critical systems where critical parts are built out of high assurance techniques and their composition is verified so that we can guarantee that there are not scaling remote attacks? And I would say the answer to that is actually yes. We have the tools, we have the technology, we know how to do this. What we're potentially lacking is the knowledge, a widespread knowledge that we can, and the willpower and the desire to actually go forward and do it. But the researchers have gotten the technology to the point where we really can now build systems that are verifiably functionally correct and of sufficient size to be useful, like the helicopter. And what this produces is a system where attackers are reduced to threat models that don't scale very well. Right? If Black Hat has to go take a rock and put it into every self-driving car that he wants to attack, then Black Hat can only affect a relatively small number of people and will be in a much safer world. Thank you very much. I'm happy to take questions.
Thank you so much. Where does property-based testing fit into the stack?
Yeah, so I think property-based testing is another nice formal methods-based technique. I mean, it's a testing-based technique, not a proof-based technique, but it helps increase the robustness of the system and make it easier to do the formal verification if you get the low-hanging fruit out with automated testing. So I think it's a good part of an overall assurance story for the software. Right? I think one of the myths of formal methods is that you have to prove absolutely everything is functionally correct all the time, and that's the only approach that's worth taking. But I think that's like not at all the case, and property-based testing is a really good another tool in the toolkit. Question?
Yeah, thank you for this success story. It's very promising. My question is DARPA investing in language research to embed verification proofs into the general programming language? Right.
So DARPA doesn't invest in technology per se. DARPA invests in solving particular problems. So in HACMs, for example, we did invest quite a bit in various programming language technologies. Domain-specific languages, for example, were used quite a bit, and tools to develop them, and connections with your improvers, things like that. But DARPA isn't interested in that technology per se. DARPA is interested in producing vehicles that aren't hackable. And so like in the US, the National Science Foundation's charter is advancing basic science, right? Do whatever you want to advance basic science. DARPA is about detecting and creating strategic surprise that has national security ramifications. So to the extent to which a particular problem that DARPA is interested in has language research as a part of it, then DARPA is investing in language research. But it's in support of doing something else. So when I was at DARPA, HACM's funded programming language research. I also created the PAML program on probabilistic programming languages that funded research in programming languages. Suresh Jagannathan did research on synthesis and mining of data repositories. So there has been a fair bit of research that DARPA has funded recently in programming languages, but it's all in the service of solving some problem that is of national strategic or international strategic importance. It's also the case that programs at DARPA are started by the program managers. So the best way to get research in a particular area funded is to have somebody who does research in that area go to DARPA and convince DARPA that we need to do this kind of research. So it's not an accident that DARPA started doing things in programming languages and formal methods when I went to DARPA and when Suresh went to DARPA. Yes?
Yeah, so I want to go on a bit about that point of the funding. As far as I got from your keynote, DARPA is active in funding formal methods, and also some companies are doing that. And if I understood correctly, there's now some sort of requirement that DARPA wants to enforce the use of formal methods somehow. Did I get that correctly?
So DARPA did the proof of concept that showed that if you use formal methods techniques, you can produce software that is much less vulnerable to attack.
Right.
So DARPA is continuing to fund other formal methods to make that more possible. Right. But again, they're not funding it to fund formal methods. They're funding it to make the vehicles. And so in terms of the mission of getting it adopted, that's the Pentagon and policy. So DARPA doesn't do policy. DARPA just does the technology, taking the technology risk off the table.
Right. So I was wondering, do you think that the non-military funding agencies are going to catch up at some point so that more civil research is being funded instead of military applications?
Yeah, so NSF is invested in formal methods nonstop, and funding agencies in Europe do even more investment in formal methods, right? COC was supported by the French National Research System for that 50-year period where there weren't very many positive results. So lots of kudos go to the French Research Authority, and similarly the Australian Research Authority that funded a lot of the work on Data 61 for very long-term research where the impact was 10, 15, 20 years down the road from what they actually did. The National Science Foundation in the US is stepping up the funding for formal methods research. They just awarded maybe a year and a half ago, they created an expedition in formal methods called DeepSpec. So expeditions are like $10 million grants given to a collection of organizations. DeepSpec is funding researchers from MIT and Princeton and University of Pennsylvania and probably a couple others to work on, indeed, specifying complex systems with complex interface boundaries and proving properties about them. So yes, I think the answer, basically the short answer is yes. Sorry about the very long answer. Sophia? Oh, sorry, there's a microphone.
So you mentioned that it took a lot of years for people to produce to prove the things they did. And you also mentioned that AWS are using some automated tools to update their proof system. So does it mean that there's a light out there showing that soon we're going to have something like automated tools which would be useful when we have active developed software to update proofs, or we just have to still spend years and years on proofs?
So I think the years and years numbers were really only true for the SEL4 and the CompCert efforts. The rest of them were consistent with the development time or less than the development time of the system. In terms of the automatically updating proofs, I think that's at the very cutting edge of the research. So I expect that will continue and will trickle down, but the trickling down will take a while. And I think the places that it will trickle down to is where there's a clear business case that the increased cost is worth it in terms of increased security. And I think the heightened awareness of the cost of security vulnerabilities and all the companies that are having to pay millions and millions of dollars to clean up breaches, I think will push back on the software industry to say, like, no, it's not okay that your software comes with no guarantees. I don't care if you guarantee that the widgets will all display properly, but you have to guarantee that the users are authenticated and the PRI data is kept private. I mean, it could be that the GDPR restrictions that just came into place, which have significant penalties for not dealing with data appropriately, will also put pressure on the software industry to produce software that has enough guarantees that it isn't just child's play to go and steal the information. So I think the economic incentives are starting to come in line so that it will be economically advantageous to have software developed to these high standards and that the technology is coming in line at the same time. So my hope is very much that in the next 10, 15 years, we will have much more verified software. And I'm not talking about we're never going to have all software be verified, but the exquisite artifacts from which you can build a system that makes it much harder to hack into, I think that we will get that. Next question, Sophia.
Thank you for a wonderful talk, and thank you for also put the work into making HACM and the good result that came out of it, the very optimistic result. You spoke about economic incentives, and you said that the whole project cost $62 million. I was wondering whether you can give any estimate of what would it take for Boeing, for instance, to develop the software for the new helicopter, and what would it cost them to make it secure in the sense that you were able to do in the HACM's project?
So HACM's was originally funded for $70 million. Not 62, and it got additional investments of somewhere on the order of $10 million to be able to extend the results to more platforms. And so one way you can tell a program is successful if they add money to it instead of taking money away. In terms of the software for Boeing to do it again on another platform, it depends on kind of how aggressive they want to be and what they want to do with it. I think replicating what we did with the unmanned little bird is actually relatively straightforward. They were able to do the tech transfer to a team of a relatively small number of Boeing engineers, maybe 3 Boeing engineers who were able to deploy the technology. So if you're just trying to replicate that in other kinds of platforms, it's relatively straightforward. If you want to verify additional parts of the system are functionally correct, like if you wanted to prove that the camera wasn't being spoofed, that it was giving you exactly the correct pictures that came back from the images, that would be a significant effort. People often ask about, well, what about autonomy in terms of cybersecurity? Like they're really worried about the security of autonomous cars. And I think that's a good thing to be worried about, but from a security perspective, autonomous cars can't do anything that normal cars can't do already that are from a security point of view. It's like the normal cars already, the acceleration, the brakes, the steering are under software control. So if an attacker can break in and take over control, the attacker can make the car do anything that the attacker wants it to do. The difference when you get autonomy is that in an unhacked state, the car is deciding what to do, and so it may or may not be doing the correct thing. If you're talking about you want to prove that the autonomous software is functionally correct, that is a super, super hard problem. I think about it, like how would you even describe what it means for a car to drive correctly? Like in all of the different weather conditions, like driving through Harvard Square where you have pedestrians walking backwards off of sidewalks so they can take a picture of Harvard, while you have bicyclists driving down between the lanes in the wrong direction. How do you even start to say what it means for that software to be correct? So proving autonomous software is functionally correct is a problem that I don't think we even know how to start. So there's basically a whole range from things that are like easy and straightforward, we already know how to do them, to we have no clue, depending on what you're talking about.
That's sadly the last question we can take. And thank you again so much for your amazing talk.
Sure, thank you very much.